talking me into giving this presentation for so long. So now it's finally done. So thanks, Juli, for that. Thanks for the space. I mean, it's a huge honor to be part of this SciMo, where so many important people of the company already been here. So that's great. Thanks, Juli, and thanks, of course, to my team at Mining, who has been helping me with this presentation. So with no further introduction, I think that we can jump to start speaking about mining, merge mining, and all that's related to it. Feel free to ask any question whenever you have them. So just to raise your hand, just write something in the chat, and I'll try to answer it as soon as possible. So that's and now let's go. So I'm going to start with Bitcoin mining before jumping to RSK merge mining, which is, of course, what brought us here. So let me see. Perfect. So let's talk a little bit about Bitcoin mining and how we're going to understand it. So Bitcoin mining, it's, as it says there, the process that allows transactions as a part of the block, which is basically the container of the transactions, to be somehow confirmed. Now we're going to define what somehow means, and then add those transactions to the Bitcoin blockchain. So in order to explain that, I thought about sharing with you the transactions road trip, let's call it in a way. So let me share my other screen, and you're going to see on my other screen that I'm going to go through all the actors that are here listed, and I'm going to explain the role of them and how they interact. So just give me one sec. Okay. Hopefully you're all seeing my presentation. Perfect. That's my blackboard. So it's the first time I use a blackboard like this with an iPad, so I don't know how it's going to work, but let's give it a try. Okay, so what I said is that I was going to talk about the actors. So who are the actors of the Bitcoin mining ecosystem? Basically, the first thing that we have here, I'm going to write it here. I'm going to do this. Is Bitcoin. Bitcoin is the Bitcoin node, right? So the Bitcoin node is the one that, as many of you know, receives the transactions from the users and then somehow transmits them in order to be added to a block. So how does that happen? So these transactions, whenever are received by the Bitcoin node, are put in what we call a pool, and the transactions over there then are ready to be included in a block. How does that happen? There is another actor here, which we're going to call I'm going to put just MP, not to write that much, but it's the mining pool, right? And the mining pool actually interacts with the Bitcoin node. And how does it interact? There is a JSON RPC interface in which the mining pool has a method that says, hey, Bitcoin node, just give me, please, all the transactions you want me to mine. Okay, so the Bitcoin node gives the transactions as a way on a method that is called getBlockTemplate, just the tech detail for the ones that are technical here. So, and that's how, in that first interaction, the mining pool receives a set of candidate transactions that will decide to add in a block. So now that the mining pool has that set of transactions, it should actually build the block. So this is very important. The Bitcoin node does not build the block. The mining pool does. So the mining pool builds the block. And once it builds the block, then it must provide it with a proof. As many of you know, up to now probably, and for those who don't, I'm going to tell you right now, these blocks need to have some kind of validation in order to be added to the blockchain, right? So this validation, it's called proof of work. And I'm going to go deep into it right now. So up to now, we have these two actors, the Bitcoin node and the mining pool. And now we have several other actors which are called, which are the mining hardware. I'm going to draw them here. So this would be the miner 1. This will be the miner 2. We have several other miners, and this will be the miner M, let's call it. So we have this, and they all interact somehow with the mining pool, and we're gonna see how. So the mining pool actually prepares the job. What we call it is the job. So basically, let me go one step backward. So the mining pool has the transactions and say, hey, I need to put this into a block. He builds a block, and then he says, well, I need a proof of work for this block. What is the proof of work? The proof of work is basically a mathematical proof that says that there has been some work done in order to show that that block is valid. So then you're going to ask, okay, but how do we know how much is enough work for this for a miner? Well, that is provided also with the from the Bitcoin node. So the Bitcoin node not only gives the transactions, but also says, hey, if you want your proof to be valid, well, you got to fulfill this condition. And that condition, it's called target. Basically, the target is a number that represents how much work must be done in order for a block to be valid. So now the mining pool has all the information. He says, okay, well, I got these transactions. I'm going to build this block, and I'm going to somehow obtain a proof of work that must fulfill this target. When I say fulfill this target, basically is the proof of work algorithm. It's a hashing algorithm. It's called double SHA-256. Probably that says a lot for some people. I mean, it's double in order to avoid an attack. That's why it's done double, not because of any other reasons. It's called the length extension attack, if I'm not wrong. So basically, once all this information is received by the mining pool, he knows that someone must do that job, must apply that algorithm, get a number, compare it to the target, and see if it works or not. So if the mining pool is not the one that does that, that's why we have the miners in here. So how does this work? So the miners interact, each of them, with the mining pool, right? Here is a protocol that we call stratum, right? And this is how the mining pool gives the least amount of information required to calculate the proof of work. And that's what the mining hardware does. The mining hardware is basically a piece of hardware that is specialized in doing one kind of calculation, double SHA-256. So they get an input, and once they get that input, they just do the hash, and then they send the results to the mining pool. They also have the ability to compare that result with the target provided by the mining pool. So whenever a mining hardware is working, they do a hash, they do another hash, one after the other, lots of hashes, and whenever they find a hash that fulfills what was required by the mining pool, they send it and they say, hey, so here I got this solution, just check if it's okay. And then the mining pool now has the block with the transactions in it, has the target, and has a possible solution for that. So once it has the solution, it just compares the solution and see if it's okay. If the solution is okay and fulfills the target, then comes the last interaction, where the mining pool actually, by the same protocol that, as I mentioned before, submits the block to the Bitcoin node, and afterwards the Bitcoin node says, hey, okay, perfect, I think you're right. It also validates all the proof of work and adds that to the network. So basically, that's how this all works. There are some details in there. For instance, I talked about target, but many people probably would have learned about difficulty. And say, well, the Bitcoin network difficulty and that kind of stuff. Well, difficulty seems to be a more intuitive way to understand how difficult it is to mine a block. And why is that? Because difficulty actually represents how more difficult it is for a miner to mine a block compared to the first target in the Bitcoin network, in the whole history. So difficulty basically is how many times it is harder to now prove that a Bitcoin block is right. Regarding the algorithm and the miners, one question that you're probably asking yourself now is, okay, so why do I need all these miners? Why did Martin actually draw m miners? Well, because as the time goes by, there are more and more people trying to actually mine Bitcoin. Why? Well, that may be for several reasons, but one reason that I can recall, it's basically that they wanna earn the rewards, the Bitcoin block rewards, as we all know. So the Bitcoin block has up to now a 12.5 Bitcoin reward whenever you find a valid proof of work. So that's a pretty good incentive for miners to actually do it. And they also get the transaction fees from all the transactions that are included in that block. So that's why we have more and more miners these days. Well, these days, since a long time, actually. So with all this being said, you're probably asking also, so how do we, so what's the main characteristic of this mining algorithm? Well, the main characteristic is that the SHA algorithm is random. So whatever so the only way to get more chances of finding a valid proof of work is to have more power, is to have more miners working on it. That's why we have all this mining hardware, or what I'm also calling miners in this talk, working together. They're working in different pieces. They work with different inputs, but the output and the goal is the same for all of them. And here, here in this drawing, what you're seeing, it's basically only one part of the big picture. So the Bitcoin mining big picture would be that there's not only one Bitcoin node, there are many of them, and there are many mining pools software also, and there are many miners all around the world. So that's basically, so I just simplified the whole picture, because I mean, if you have one or you have 10, then it's the same, but it's important for you to also understand this. So that's basically that's basically Bitcoin mining explained. Let me change to my other screen, while in the meantime, if you have any questions, this is a good time. So now that we all know what's the goal of Bitcoin mining, where are the actors, we've seen them here, and now we've been through some key concepts, basically, which are the algorithm, the proof of work, the target, and the difficulty. And now, fortunately, I wrote all these concepts here in order to remember which ones I didn't mention in the drawing. So let me talk a little bit more about them. So now you're probably, another question that is important is, okay, but if you have more miners, then you have more people working on the network in order to get a valid proof of work. So then why does that not affect the periodicity of the Bitcoin blocks produced? Well, because Bitcoin also has something that is called difficulty adjustment. So that's why the difficulty in Bitcoin is not the same as the one that was for the first block, and it's way higher right now. Because Bitcoin has a target that is to produce a block every 10 minutes. So this difficulty, or this target, actually, the one that I mentioned, changes and gets adjusted every time a block is received. Well, technically every 2055 blocks, but it's the same thing. It's the same concept that's behind that. So that's in order to avoid to have Bitcoin blocks every 1 minute. So what the Bitcoin node knows how to do is to say, well, okay, I'm getting a huge amount of blocks because I have tons of miners now doing a great job. So how am I going to stop this? Because I need to be sure that I'm going to be receiving blocks one every 10 minutes. Well, I'm going to put a higher difficulty. So now that I have a higher difficulty, then these guys will have to work more in order to get a solution to my block. And that's what we call difficulty or target adjustment. As I already mentioned, difficulty, it's a formula that comes from the target, so it's the same to talk about them. So that's pretty much what the Bitcoin node does. And then that sends that information to the mining pool. Another important thing is, and you're gonna hear me talking about it very soon probably, it's the hash rate, the network hash rate. What does it mean? Well, the mining hardware, as I already mentioned, it's a machine that knows how to do hashes, basically. So, and how many hashes it does per second or per minute or however you wanna measure it, it's called the hash rate. So each of the miners does a number of operations per minute. That's the hash rate of each miner. But then if we sum up the hash rate from all the miners in the network, then we get the network hash rate. And that's what we're gonna refer in the future. And probably whenever you enter to a Bitcoin network stats, you're gonna see that you have there the hash rate of the network, or the hashing power also called. And you're gonna see that, well, right now it's probably 100 exahashes or something like that. But it's that's the number you see over there. So that's pretty much all how Bitcoin mining works. I don't know if you have any questions. I'm gonna check the. So okay, I'm just checking the chat. Okay, well, apparently we're good to go. So, and now the moment that you've all been waiting, I'm pretty sure, RSK merge mining. So now that we all know how to do merge mining, how to do mining actually. Okay, I'll let the discussion go without me in the chat. So let's go back to what I was saying. So RSK merge mining, it has a goal. You probably noticed that the goal is pretty much the same as Bitcoin mining, which is allow transactions as part of the block to be confirmed and then added to the RSK blockchain. But it's a different implementation, as you probably already imagined. So the goal of RSK merge mining is basically a process that allows the RSK blockchain to be mined simultaneously with the Bitcoin blockchain. And this is like what we sometimes call the magic of merge mining. I mean, basically merge mining allows you to use the same hashing power and the same work that has been done by the mining pool and the mining hardware to get a valid proof of work for another network. That's merge mining. In this case, when we talk about RSK merge mining, is that with the same work that it's done for Bitcoin, which we usually call primary chain, we get a valid work for a secondary chain, which in this case, it's RSK. As you may see here, we have different actors also. Well, the same 3 actors that I've shown before, but there is a new one, which is called the RSK node. We all know that one. The same way as before, I'm gonna talk about a few key concepts while I do a drawing where I explain how this new actor, which is the RSK node, interacts with the other actors and how does his participation makes merge mining possible. So let me share my other screen once again. Whoop. There it is. Hold on a minute. Too much sun coming from my window. So, as you may remember, we have here the Bitcoin node, right? We have here the mining pool. I'm gonna put pool this time, right? And here we have the miners. Miner 1, miner 2. Perfect. And they all talk between themselves, as we already learned how they do it. You have this and the block submission. So now there is a new actor. This new actor is the RSK node, which is here, right? So the responsibility of the RSK node, some of you may say it's the same as the Bitcoin node, but it's not. I would say it's pretty much the same in some aspects. So if you remember, the Bitcoin node was the one that received transactions and sent them all to the mining pool. Well, the RSK node receives transactions, of course, from the users, but the main difference is that it also builds the block. Do you remember that the building the block responsibility for Bitcoin was in the mining pool? Well, right now it's on RSK over here. So let me, there it is. So how does that work? So the RSK node receives transactions and puts them all in a pool the same way as the Bitcoin node, but here it also builds a block. And then when the mining pool asks for work to the RSK node, then the RSK node does not send the block or the transactions. It just sends something that represents it, which is a hash, basically. So the RSK node, so the mining pool says to the RSK node, hey, please send me some work to do. And the RSK node sends that work. And what it sends over there, it just sends a hash plus a target, right? Target. There is. This hash, it's what we call in RSK the hash for merge mining. Why this is called the hash for merge mining? Because in RSK, in different instances of the block of the transactions and the block production, let's call it in a way, we have two different kinds of blocks. Whenever you build a block for mining, that's what we call the mining block. Why? Because the mining block is not the same block that will end being added in the main chain after the proof of work. You're going to see why I'm telling that. But for now, the important thing is that you have a block that has been built inside RSK, a hash that represents that block, which is called hash for merge mining, and a target that it's basically the same as in Bitcoin. Whenever you want to, because RSK uses the same proof of work algorithm, that's a condition in order to do merge mining, to use the same proof of work algorithm. So RSK uses the same proof of work algorithm as Bitcoin, which we know that is SHA-256. So now RSK got the transactions, built the mining block, then got a hash for that block, which is a hash for merge mining, and a target, and sent that to the mining pool, and said to the pool, hey, well, perfect. Now you have all the information required to do merge mining. And the pool says, okay, perfect. What do I have now? I have the Bitcoin block that I already built with the transactions, and I have all this information from RSK. So how do I link this information? And this is one of the most important parts of merge mining. So basically, the way this information is linked is if you add something to a block, to a Bitcoin block, somewhere in the Bitcoin block, and you get a valid proof of work for that, then all that information is supported by that proof of work. So basically, if we add something that links us to the RSK block in the Bitcoin block, we may have something that is as valid as, with a valid proof of work, as the one that has the Bitcoin block. So that's basically what merge mining does. Merge mining says, okay, I have this hash that represents the RSK mining block. And I'm going to put that hash somewhere in the Bitcoin block. So whenever I get a valid proof of work for this block, then I'm going to use it for both Bitcoin and RSK. I'm going to prove both at the same time. So, and now comes a little bit of the technical details of where does that go. Well, that hash is added to the, let me go back to the other presentation for a while. Okay, here it is. So as you may see here in the mining pool section, that it's what we call the information. It's called the world famous tag for merge mining. That's how we like to call it, which is basically in the Coinbase transaction of the Bitcoin block. The Coinbase transaction is the first transaction of the block, and it's the one that has different outputs. One of the outputs says the address of the miner that's going to get the block reward, and the other outputs are not in use unless you do merge mining. So whenever you do merge mining, you just add another output to the Coinbase of the Bitcoin transaction and say, hey, I get a hash from you, which is a 32 bytes hash. Just add this output with the following identifier, which is RSK block, and then just put the hash that I already give you, which basically represents 20 bytes of the mining block and some armadillo info, which I'm not going to go deep into that on this talk. But just imagine that this is a 32 bytes hash, and that's what represents and identifies the RSK block. So the RSK block was already built, was already sent to the mining pool, and the mining pool now knows how to add that block into the whole Bitcoin flow that he already had. Actually, what he was conceived for was for mining Bitcoin. So from here on, let me resume this again. So from here on, what we already seen is that we had Bitcoin over here. Well, that was a little bit big. Bitcoin, the mining pool, and the miners, we all know how all that works. Now we know how RSK works, and now we know that RSK provides work to the mining pool over here. And once we have the mining pool over here, we know that he adds this RSK block plus the hash to the Bitcoin block. And all that goes to the information provided to the miners. So the miners start working again in search of a proof of work. And whenever they find a proof of work, they send it valid to the mining pool. And the mining pool does the same thing as it used to do before. It says, hey, well, I got a Bitcoin solution, I'm going to send it to Bitcoin. I got an RSK solution, I'm going to send it to RSK. But this is not the only case that may happen, and this is another very important part in merge mining. Why? Because as we all know now, the difficulty of RSK is lower than the difficulty of Bitcoin, because we don't have all the miners working in Bitcoin working in RSK for merge mining. So if the difficulty is lower, then that means that getting a valid proof of work for RSK would probably be easier for the miners than what it is for Bitcoin, right? So how does that work? So I said that RSK sends a target over here, and Bitcoin also sends a target. Well, the fact is that, I'm going to write it here if it fits, that the RSK target, right, it's lower to the Bitcoin target, okay? And this is important also. This is not a player, but this is important. So we do have the RSK target that is lower to the Bitcoin target. So whenever a miner finds a solution, then that solution gets compared with the RSK target and the Bitcoin target. And that solution may be valid for both, if it's a good one, or not. It may be only valid for RSK, or may not be valid for any of them. And here here's a third dimension. There are three different kinds of targets or difficulties in here. I already explained two. The one that is required by the RSK network and the one that is required by the Bitcoin network. But since these numbers are super big and these solutions are hard to find, the mining pool needs to know that the miners are actually working. And since it's so hard to find a solution, if we use the same RSK target or the Bitcoin target to send from the mining pool to the miners, they would send a solution probably once every 10 years. And that doesn't seem to be a good idea. So we have here, between the mining pool and the miners, a new difficulty, which is called the pool difficulty. which is way lower than the RSK and the Bitcoin difficulty. Unfortunately, I don't know if it's going to fit here. Probably not. So you have the pool target or the pool difficulty is the same thing, which is very, very lower. And why so what does the pool does with this? So basically the pool wants the miner to send him shares, which are to send him proof of works candidates. So what it does is that it just puts a super low difficulty in order to receive a certain number of solutions, of proof of work valid solutions per minute. Let's say it's usually 6, and the difficulty it's super low. It's usually 32,000, something like that. So the pool, so now we have a flow of the pool generating different solutions every, let's say, 10 seconds. And then whenever one of those solutions gets to the pool, then it gets compared to the RSK target, to the Bitcoin target, and if it works, then it gets submitted. But the main question here is, okay, so you are asking for a lower difficulty. If you're asking for a lower difficulty, how does that difficulty can fulfill the higher difficulty? Well, the explanation to that, it's basically that the algorithm, the hashing algorithm, it's random. Since it's random, whenever you have something that it's higher than 32,000, which is the pool difficulty, it may be also higher than the RSK difficulty, but not as higher as required by Bitcoin. So that's pretty much how this difficulty thing works, and that's how merge mining actually works. Because if it wasn't from the if it wasn't for this difficulty, the mining pool difficulty, then it would be very hard for the miners to send shares periodically. That's what we usually call the magic of merge mining. Now I'm going to go deep into how RSK actually stores that solution and allows it to be validated in the blocks. But up to here, I want to know if it's clear, if you have any questions about these difficulties. It's so Fede, you can actually talk. I would like to.
So yeah. So this new difficulty, it's kind of like a filter for mining for concurrency, let's say. So they don't say they don't send all the time proof of works hashes.
Exactly, it's a number that actually has
limit.
That's exactly, because okay. they can, if the miners have if the mining pool sends a super low difficulty to the miners, then the miners are going to lose the mining pool.
Send all the time, and it can get anyone.
Yeah, exactly, and I mean, and the network is not going to support that. So that's why they always, I mean, 32,000. But if you have many miners, it's probably more. This number is also adjusted by the mining pool in order to receive a number of shares, a number of solutions per minute. That's basically what. So the same way as Bitcoin, as I said, that Bitcoin actually says, hey, I want to block every 10 minutes, so I'm going to just adjust the difficulty. The mining pool does the same with its miners. When it has more miners, say, hey, you're flooding me, stop it. I'm going to just lower the difficulty.
Just to prevent flooding, as you said.
Just to prevent flooding and to actually know how many miners are, and just to know that the miners are still alive, basically. That's what they.
Okay.
Because then we're gonna go a little bit deeper into the economics behind that and why it's important for the miners to be always sending shares.
Okay. So ideally, this difficulty should match the block difficulty. Ideally, I mean, just
actually,
if there is any concurrency problem, let's say, if the mining pool could attend all the miners, this kind of difficulty shouldn't exist, let's say.
No, because this difficulty, it's one per miner, because each miner has a different connection with the pool. So what they are trying to adjust is the solutions provided by one miner, the other, and the other.
Okay.
That depends on two factors. One factor is the one that you said, I don't want to be flooded. That's what the mining pool says. And the other factor is basically, I want to get this amount of solutions per minute or whatever. So
okay, got it.
So, and then you got the three difficulties that we were talking. So we were talking about the pool difficulty, which is super low. Then you have the RSK difficulty, which is a little bit higher. And then you have the Bitcoin difficulty, which is way higher.
Okay.
One thing that you're probably asking yourself is also, so now in RSK, we have one block every 30 seconds. At least that's what we want to have. So how do we deal with that? How does it affect the difficulty? Well, basically, the difficulty gets adjusted on a different way than Bitcoin. So the formula is different in order to have 30 seconds blocks instead of 10 minutes block. That's pretty much what RSK does. So it's not, so the RSK adjustment difficulty, it does not only gets influenced by the fact that we want to have 30 seconds block, but also by the fact that we don't have as many hashing power as Bitcoin. So those are the two things that mostly impact the calculation of the RSK target or difficulty, as I already said. So being all this said, where we are now. So now we said, okay, now we know how RSK receives transactions, how does it talks to the pool to send the work. The pool knows how to add that piece of information from RSK into the Bitcoin block, then sends that to the miners send solutions, and once they get here, so the pool submits. If the solution fulfills Bitcoin, then it submits a solution to Bitcoin. If it doesn't, then it just checks and see if it's a solution for RSK. If it's a solution for RSK, it sends a block to RSK. Well, technically not a block. So it sends different pieces of information, which I'm going to talk right now. I'm going to resume the presentation over here. Okay, so here we are. So what we said now is that, just doing a quick recap. So we have the RSK block, mining block, which is created inside the RSK node, and it's represented by the hash of burst mining. That's what's sent to the mining pool. Then we have the mining pool, which has the tag, and the tag gets added into the Coinbase transaction of Bitcoin. Then we have the difficulty magic, which is basically the three difficulty values I already explained. I'm going to talk about this later because it's just a detail, and I'm going to focus a little bit more on what the RSK node receives whenever the pool finds a valid proof of work solution. So the RSK node receives from the pool three pieces of information: the Bitcoin block header, the Bitcoin Coinbase transaction, which contains the RSK block and the 32 bytes hash, and the Bitcoin Merkle proof. Why are we sending this to the RSK block? Well, because, as I said before, the RSK block needs to know that the information inside the Bitcoin block has a valid proof of work. In order to know that, what is the process? Well, that's what I'm gonna talk about you right now. Let me create a new node. There it is, and share it to you. Okay, here we are. So what I said is, we got the Bitcoin Coinbase transaction, the Bitcoin Merkle proof, and the Bitcoin header. What is that, and what information do we extract from there? So let's think about the Bitcoin header as this, basically. This is the Bitcoin header, right? And it has several fields over here, as many of you know. So there is the target, there is some information about transactions that we're going to use now, and all that stuff. So the Bitcoin, this is the Bitcoin header. Then we have also the Coinbase transaction, right? Which I'm going to put it here, like this. And somewhere inside the Coinbase transaction, we do have what we already said, which is RSK block. And then bytes, right? And more bytes. So this is the Coinbase transaction, right? And then we got the market proof. So what is a market proof, and how is it provided to the RSK node? Well, that's actually the how can I say? It's a partial Merkle tree. For those who don't know what a Merkle tree is, it's basically a tree where its keys are hashes. So I'm going to write that in here. So a partial Merkle tree is something like this. You have some piece of information here, which is hash. You have another one here. And then if you hash them, you get a hash here. And then you just hash this with whatever it's on the other side of the tree. What do I mean? Here you have another tree, which is represented by a hash, and then you just match them both and get a hash here. So this in here, I'm gonna do it like this. This is what we call a Merkle tree, like a full Merkle tree, right? And this thing in here, up here, is what we call the Merkle root, right? And where is the Merkle root contained? Well, the Merkle root is contained in here, in the Bitcoin header, right? So now that we got this Merkle tree, what sense it's basically a partial Merkle tree, but it doesn't matter for the purpose of what I'm trying to explain. So just remember that it's a partial Merkle tree and not the whole tree, but it's the same thing. So now we have these three pieces of information in the RSK node. Okay, so the RSK node basically receives this and says, okay, well, what I'm going to do first, I'm going to check the Coinbase transaction to see if it has the hash for merge mining. If it has the hash for merge mining, I'm going to look for the blocks that I already built and check if those blocks were built by me, just in case someone is attacking me or someone is sending me information that that I haven't generated previously. So best case scenario, you get an RSK block with a hash, you go to the list of pending blocks you built and say, hey, well, perfect. This is the mining block that I built and matches this RSK block that I'm getting in a Bitcoin, in this Bitcoin information. Okay, perfect. Let's validate this and see if it actually can be built into a chain block, what I call chain block for RSK. Chain block for RSK is the block that ends in the blockchain, basically. Either in the main chain, or it's either an anchor or a sibling or something like that. So we already know how the RSK node received this information and matched this with the block that you previously generated and sent to the mining pool. Now that we have this information, we want to know that this block fulfills the proof of work. And how do we do that? Well, in order to do that, we need to validate that the difficulty in the Bitcoin header and the proof of work also provided in the Bitcoin header is valid and it fulfills the difficulty that the RSK block provided. And that's pretty much it. It's a proof of work validation. That's what it does. But now you're probably thinking, okay, this guy is sending me a Bitcoin header and a Coinbase transaction, and I'm extracting information from both of them. So wait a minute. What if the Coinbase transaction does not belong to the Bitcoin header? Well, if that happens, then we have an issue. Then someone is is trying to attack us, or it doesn't have the good intentions at least. So how are we going to validate this? That's why we do have the Merkle tree here. The Merkle tree here, there it is. Since we have the Merkle tree over there, what we know is that the transactions have a predefined order, and the Coinbase transaction is always this one here, right? So with the Coinbase transaction that we get over here and the partial Merkle tree provided by the mining pool, then we can get the Merkle root. And if that Merkle root matches the Bitcoin header, then we can assure that the Coinbase transaction provided by the miner actually belongs to that Bitcoin header. So whenever we have that, we can say, okay, I got something that actually is okay with the difficulty I asked, and it matches the block that I built. So I'm good to go. And what does that mean? Well, as I said before, we built a block which was the mining block in RSK. How do we move from the mining block to the chain block, the one you actually find in RSK blockchain? Well, by adding these 3 pieces of information. You just add over there the Bitcoin header, the Coinbase transaction, and the partial Merkle root, Merkle tree, in order to get the Merkle proof, and that's what builds the Bitcoin block. That's basically what you will find in RSK chain. So that's why I always say that inside the RSK node, it depends on which phase you are. Then you have 2 blocks: the one that is waiting to be mined, the mining block, and the full chain block, the one that has the valid mining information. And what does this allow? Well, this not only allows for the RSK node to validate it and all the RSK nodes. I mean, you can just check any RSK block you want, get these 3 fields, and you'll see that it has a valid proof of work and that the Coinbase matches. So this is the last step of the whole merge mining trip, where well, I hope you understood how this all works and how this all actually builds on top or on a side of Bitcoin mining. But this is not the end. We still got more. Let me go back to the presenting over here at my laptop. So these are the key concepts, where there is a little thing that I forgot to mention, that it's basically that it's not a minor thing. I mean, it's important for the pools, and it's a question that many people usually ask is, okay, well, so you're asking the pool to do merge mining right now. So how do I know that doing this merge mining thing, you won't be affecting the pool's performance? I mean, because I'm mining Bitcoin, I don't want to lose any Bitcoins that I mine because of your merge mining. That's what they usually say. Well, we've done several tests that actually prove that the pool works fine, even when it's working at a faster pace. What do I mean with a faster pace? As we all know by now, the pool actually gets a 10-minute, was conceived to build a 10-minute work for Bitcoin. And that work usually gets refreshed every 30 or 55 seconds for Bitcoin inside the pool. So the pool sends to the miners new work every 30 or 55 seconds, just in order to be able to catch new transactions. That's the main goal. That's why it does it. But you're saying, okay, so now we have a problem, because RSK wants to build blocks every 30 seconds, and I'm updating the job every 30 seconds. So there's something that's not right over there. I mean, this probably won't fulfill the average block time that the RSK network wants. So what we did for all the pools, and what the pools that are doing merge mining with us are doing right now, it's basically to refresh the work at a faster pace. That's what they need to do. And once they refresh the work at a faster pace, they need to also update it whenever they get a new RSK work, in order to actually added to the Coinbase transaction. Otherwise, they will be working on an old job that is not gonna, well, it's actually gonna pay some reward, but it's not gonna be a main chain block probably. So that's the other thing that is very important in merge mining. If someone asks, okay, now you're asking the pool to do more things and to work at a faster pace, then the answer is yes, we're asking that. And the answer is we've been doing a huge amount of tests that proves that the pool supports being interrupted at that faster pace, and the same goes for the mining hardware. So that's the last and I would say the performance side from all the merge mining that we've been explaining. And this is a good time, since I explained a lot of things, to ask questions. Then I'm going to show you how you can actually prove that merge mining works to your friends. But now it's a good time for questions. Raul, you are the last one, so you can make that out loud.
Okay, so the part that I maybe didn't understand is this faster pace that we require means asking the mining pool to send work refresh at shorter intervals, so faster, or if not, what do you mean?
That's what it means.
Okay,
thanks for making that clear, because for me it was like, yeah, it's this, but yeah, it's I mean, instead of refreshing the work every 30 seconds, they can actually, this is a configuration setting, they can actually choose to generate the work every time they get a new RSK block, or every time they know that RSK has a new block in the network.
Nice, thank you.
Perfect. Okay. So I think that now we are entering on the last phase of the presentation. So if you want to show this to your friends, you're probably saying, okay, Tincho, perfect. You told me that you're adding stuff into the Bitcoin Coinbase. So how can I actually check for that? So you can check it like this. I don't know if you see my my Google Chrome.
Just the presentation.
No. Just the presentation? Okay.
Yeah.
So let me present my full screen then. There it is. So what I did is I clicked on Bitcoin block and it sent me over here. This is a Bitcoin block of one of our friends, /pool, that is doing merge mining with us. Here you got the transactions, right? And one of those transactions is the Coinbase, which is the first one. And then you got all the other transactions, right? So let's check what's inside the Coinbase transaction. Okay, perfect. This is the Coinbase transaction, mined by /, and the outputs that I already mentioned. Okay, so in these outputs, you have this piece of information over here, which is the merge mining RSK block and the hash. How do I know that? Because I know that the RSK block is translated to 52, 53 in hex. Up to now, that's something that I learned by memory. But I'm gonna show you that the hash actually matches with a block in RSK. So you have the hash over here. You just click RSK block, and you jump here. And this is the miner in RSK, and this is the hash. So hopefully this should be somewhere in here. Let me see if I can. Apparently not. Oh. The demo sometimes fails when you do it live. Probably I just pointed out to the wrong miner, but well, believe me, that this is the RSK block, this is the hash of RSK actually, and some other information. I will fix it for the final presentation, of course. And then whenever you got that block, do you remember the fields, the specific fields for merge mining that I mentioned? Well, you can check them here. You just come to the block, and here is the hash for merge mining, the Merkle proof, the Coinbase transaction, and the Bitcoin block header. These are all the piece of information that for that block that was supposed to be this one, but apparently it's not. And then when we talk about hashing power, what we do have is the stats, of course. You can just jump here and see how many miners do we have. Well, we actually have 58 that 2 exahashes doing merge mining with RSK, which is amazing. And this is, and compared to the Bitcoin network, we have over 60% of the hashing power of the Bitcoin network right now. Well, 62, perfect. My friends, the miners, definitely turn on some of their tools for this presentation. So this is how you can actually show anyone about the RSK merge mining information that's public. Then I think that we are, I don't know, Juli, if I have 5 more minutes.
Yes, of course.
Thank you. So I want to just discuss a couple of concepts that I think that are interesting from the mining pool side. So basically, RSK network hashing power. Well, RSK network hashing power is something that, of course, it's super important because it secures the network. But I'm not going to show anymore, so I'm going to go back to the presentation. There it is. So the RSK network hashing power, how do you should usually read that? So, well, you should understand it this way. It's super important to understand how much of the Bitcoin hashing power is currently mining us, and it's also important to understand how that is distributed. Right now, we don't have a public way to show it, but we do monitor that also. And why is this? Because if now we have a 60% of the Bitcoin network doing merge mining with us, then that's way better than having, for instance, a 20% of the Bitcoin network mining us. Why? Because if we do have the 20%, then it would just require for any participant in the Bitcoin network to get a little bit more of the 20% that they have, or actually a little bit more of the 10%, in order to start building a parallel blockchain from RSK and attack us. So now, if someone wants to start attacking us, then they probably need to have more than the 30% of the 30-ish% of the RSK hashing power right now, which is more difficult, as I said, than getting the 10%. That's why that number should always be as high as possible, and that's what we work to obtain in the mining team mainly. A couple of notes about the mining hardware. So the mining hardware hasn't always been like this. I mean, now we all talk about mining hardware, and it probably pretty comes to our mind and say, hell yeah, that piece of hardware over there in the corner that just knows how to do SHA-256. Well, at the beginning of times, Bitcoin was conceived to be mined by CPUs, but as soon as more and more power was required, CPUs were not enough, and that's how that road took us to actually having mining specialized hardware, which is, depending on the model you get, quite expensive. And these days it's around 70 terahashes per second what one of those guys can do, which is a lot. I mean, the one we have at the office, for instance, only does 13 terahashes per second. So, and that keeps evolving always, and it's also important in the economics of Bitcoin because it just ensures that these people, they spent a lot of money to buy those machines, so they probably won't turn them off in order to just because they are losing money or something like that. They will probably keep to their investment and try to earn as much as possible. That's why that's the important role of the mining hardware in all this. Though it has the counterpart that right now it's not as decentralized as Satoshi probably would have expected to be in the beginning, because there are many people with lots of these machines and huge investment in mining. But that's another discussion. Though these are all things that I'm just probably speaking on a high level, but this is just in order for you to know that we can either make another talk, or you can reach me and say, hey, I want to talk about mining hardware. I mean, because I'm curious, what can you tell me? Well, I can tell you this and a little bit more probably. And the same about the mining pools. Mining pools is a very interesting business. It's what I would call a union probably, because they just join different people. I mean, different mining hardware that belongs to different people or not. So the business of mining pools, it's basically, I just orchestrate your work, guys. You all get together into this mission that it's basically getting a valid proof of work. And whenever one of you gets that, then I'm the responsible for sharing the rewards with all of you. So the mining pools are basically that. It's basically, let's suppose that I have a mining hardware in my apartment. Then Julian has also one, and there is also one at the office. So we just all join in a mining pool, and we are actually multiplying by 3 our chances of getting a valid proof of work for a Bitcoin block. Of course, 3 these days, it's not going to be enough. We're going to probably die twice before that happens. But well, that's kind of the idea of having mining pools, and that's the role of mining pools these days. In order to, I mean, of course, they don't do it for free. So in order to maintain their business and get some earnings, they usually get between 1.5 and 3% of all the rewards that are earned by the blocks they mine. So that's pretty much about the mining pools. And now, is there any question about these topics?
So the pools are only for, like you said, like you and I having a machine in our apartments, and like those big farms in countryside in China, they don't join pools, right? They are their own thing.
Well, that's a good question. Actually, the answer is they can do both. I mean, they can say, well, we have this huge mining farm in China. Let's just work together and don't let anybody else come and work with us. Or they can say, well, let's set up a pool and invite you and me and Julian to join our pool, so we have more workforce.
Okay.
Thanks, Juliana, for the answer over there. And regarding, so that's pretty much it about the concept. I don't want to go too far, so because I'm running out of time. So the mining resources are here. Then Julian is going to share the presentation, so you can go to our site, which is mining.rsk.co. And then if you want to know a little bit more, then you go to the developer portal over here, where you have pretty much the things that I already explained about how to build a block, where does it go in the Coinbase, the possible outcomes when a miner sends a valid proof of work, and how to set up an RSK mining node and all that stuff. I mean, the developer portal is also linked from mining.rsk.co, so that's where you're gonna find all this. This was an introductory talk, so I didn't go that deep into some details, which may be interesting also. But I just try to keep it short and concise for understanding basically Bitcoin mining and RSK merge mining. So I really hope you all enjoyed, you all understood what I said. And last but not least, Julian asked me to please share this feedback with you, this feedback form. So if you can please take 1 minute and enter to this URL, which I'm gonna try to paste somehow. Okay. Apparently I can't open it here, but probably I will be able to copy that. Oh, you can scan the QR code also. Let me know if that works. Well, I don't have pretty much to say. I'm open to questions, of course, and thank you very much for attending. I mean, it's been a lot of people here, so I'm pretty proud of that. Thanks, Juli, again for the opportunity.
Thank you, Tincho. It was an interesting talk, and it's a lot of information. I have a question too about merge mining. The first one is it possible to...
I'm glad it's about that.
Okay. Is it possible to mine just in RSK?
Good question. So technically it is. I mean, we don't have in a specific piece of code to say, well, let's do it by using this. But the thing is that even if it's possible, then it probably wouldn't make any sense, because merge mining means using the same work you're doing for Bitcoin for RSK. So if you're mining RSK, why not try to mine Bitcoin? I mean, you're not losing anything. No. There's no performance loss.
No, probably you will lose rewards because you are mining RSK because you are mining Bitcoin, right? Not otherwise.
Okay.
But, Julian, you mean not mining Bitcoin?
Yes, just in RSK.
But we use Bitcoin because of the security of Bitcoin, right? So if they lose miners, it gets less secure, I suppose. And so we get less secure.
Okay.
Saying is that if someone wants to just mine RSK, one person would mine just RSK and not Bitcoin.
Right.
You could,
Yeah, basically, you
set up the node to. Sorry, Nacho. Go on.
No, go ahead. Go ahead.
All right. When you set up the node to run on Rectest, a Rectest network, a development network, it's actually mining blocks, RSK blocks. The problem you have is, well, the difficulty. So you could try to set up a node, a mainnet RSK node to mine, but it won't. It will take several years to reach the desired to meet the target to actually have a proof of work for RSK. So it doesn't make any sense, as Tincho says, since it's more a matter of the actors, the players you are competing against, rather than something of if it's possible or not. So the more sensible option is to just hop on a mining pool, an existing mining pool, and just mine there. Or if you like, maybe set up your own mining pool and mine Bitcoin as well as RSK, so you at least get a slight chance of mining a Bitcoin node, so a Bitcoin block. So that's more or less the idea. But you could actually mine only RSK.
Okay. I don't have any more questions.
I'm open to questions from anyone else that it's not Julian also.
There is a question in the chat. How much hardware is needed to run a Bitcoin node and RSK node? Probably you know the answer, guys, because I don't remember if we need too much power. What we need is more database, probably. But maybe you know the answer, guys.
How much hardware is needed to run actually a Bitcoin on an RSK node? Well, those are two. I mean, what we usually recommend is to put them into different servers, and one for the Bitcoin node and one for the RSK node, and that's pretty much it. And then it depends. I mean, if you were talking about mining hardware, then there are calculators everywhere that will tell you how much money you will earn depending on the hashing power you buy. So we even have one at the mining rsk.co website. So that's pretty much it. Usually the mining pools, you don't set up a mining pool, you just connect to one. But if you're a mining pool, then you need to have these two nodes running, the Bitcoin and the RSK.
Tincho, is it possible to buy RSK hashing power? Because I've seen that in other networks. Is it possible? Are we available for that, or
buy
not?
Hashing power?
Yeah, for RSK.
Well, I can.
Because I don't remember the page, the name.
Yeah, there are several. Nice hash, for instance.
Yeah, nice hash, that one.
Okay, so here you have two options. So either the first one is, I can offer you a miner that's at the office.
Just wondering. I know that it's not an interesting
Maybe
question.
if you want a little bit more of hashing power, then you can go to one of those pages, buy hashing power, and point it to the pools that are actually doing merge mining.
Okay.
Which are /pool, F2pool, which other one? BTC.com. Then you also have, I'm missing one, pooling. So those are the main players that are actually doing merge mining with RSK. So you just buy the hashing power there, plug it to their pools, and you're mining Bitcoin and RSK at the same time.
Okay, so is it possible? Thanks.
I have a question. Sorry, I got confused with the two servers response. So I understood that the Bitcoin, the RSKJ was a plugin. So now that you mentioned two servers, I got confused.
Oh, no. No, what I meant is that you need one server for the Bitcoin node, one server for the RSK node, and then you need somewhere else a mining pool software. If you're a pool, you need the mining pool software installed and with the merge mining capabilities, which we usually call it a plugin, but it's not. Technically, there are just lines of code that you need to merge to your pool.
Okay. And what do I need to have the two nodes in separate machines? So what are the reasons?
Just because we want to make sure that the RSK node, which uses more resources than the Bitcoin node, they don't have any conflict. We haven't been able to run a full performance test of what happens when they both work together. That's why we usually recommend just put them on different machines, and that's going to work.
Okay.
I had a question.
Yes, hey.
Yeah, just the stats page talks about total hashing power, that's a 60%, but it does not say how many different mining pools are involved. Is it 3 pools, or do you not worry about that distribution?
Of course, yes. So when I said, well, one of our goals is to get as much hashing power as we can, the other thing is to have as many different miners as we can. Because if we get 30% out of 2 miners, and that's a problem because one of the miners may get mad one day, and they can attack us very easily. So right now, that's 60% is distributed in 5 mining pools. I mean, we're working on a tool to expose that publicly, but for now, we just have it on our monitoring tools internally.
So Tincho, 5 mining pools have the 60% of the Bitcoin total hashing power.
Yes, that's right.
Okay.
The big ones.
Juli, I think we are good to go.
Yep.
Well, nice presentation, Tincho. Congratulations. You and the mining team.
Okay, thank you, Tincho.
Thank you.
Thank you.
Thank you.
Thank
very
you.
much.
Bye.
Thank you, guys.
Thanks.
Bye-bye.
Bye.
See ya.
Okay. See you.
Bye bye.